Welcome back, everybody, to the video series for Healthcare Stats, Math 146. All right, today we're going to talk about Module 5. So we're getting into probability today. Probability. I would say that the likelihood is high that we're going to talk about probability today. Badoonch. All right. So, what is the probability of an experiment or a trial? The likelihood, it's the likelihood of an outcome that is random. Okay, the event needs to be random. We can't be controlling it. So if we're throwing a die, we can't weight the die. If we are throwing a coin, it can't be a strange or oddly shaped or weighted coin. Okay, so the last example is flipping a coin, especially when we're talking about theoretical probability. So rolling of a die. Now, if you're not familiar with what we mean when we say rolling of a die, die is singular for dice. So if you've ever played any kind of a game like Monopoly or any of those games that have dice, it's a cube. It's a three-dimensional cube with 6 sides, and each side has a certain number of holes drilled into it. There's one side that has 1 hole drilled. Another side has 4. Another has 5. Another has 6, 3, and 2. So there's 1, 2, 3, 4, 5, 6. So the outcomes we would just call them 1 through 6. And of course, you know what a coin is. A coin is basically it's a cylinder that's that's not very deep, right? That has a face and it has a particular, monetary value, say nickel, 5 cents. And it has a head, which usually it's a president's head, and it has a tail, which is usually the mansion that that president lived in or something like that. A raffle ticket. So if you know what a raffle ticket is, it's like a lottery ticket. It says keep this coupon, right? It's a little piece of cardboard or paper that says keep this coupon. And then they draw a raffle. It has a number on it. Let's say 1, 2, 3. And if they call your number 1, 2, 3, then you won the raffle. Okay, some vocabulary here that we need to talk about. When I say outcome, all right, so an outcome is a result when you do a trial or an experiment. Okay, so if you think about what is the outcome when you roll a die, well, the outcomes here are, some of the outcomes are 1, 2, 3, 4, 5, 6. And by the way, the picture that I've drawn here corresponds to the number 1 because it means that the 1 is facing up. You know that when you roll a die, it has to face, the number that you're looking for has to face up. Okay, but there's also other outcomes that we could talk about, like even numbers. What are the outcomes for evens? Well, for 1 through 6, evens are 2, 4, and 6. Okay, you could talk about odd. You could talk about 1 through 3. You could talk about 4 through 6. There's all kinds of events or outcomes here. The outcomes I have listed here, these are set bars, by the way, and they're listed in between with commas. These are called simple outcomes. So a simple outcome is an example of an outcome, or simple event, right, is an example of an event that can't be broken down any further. So odd can be broken down further because it could be a 1, a 3, or a 5, or in other examples 7, 9, 11, and so on. But 1 cannot be broken down any further. It represents that picture right there. Okay, so 4 would be if that side is on top, the side with the 4. All right, moving on. So a sample space. A sample space is basically the all possible simple events, right? All possible simple events that can occur. So if the raffle ticket numbers go from 1 to 999, so let's say there's 999 raffle tickets, then the sample space for the raffle example, S, is equal to the ticket that says 001, 002, all the way up through 999. So that's the sample space for the raffle. Okay. Just erase that so we can read what's going on here. All right. So an event is simply a subset of the sample space. Just so we're clear when what we mean when we say a subset of something. If I use a Venn diagram here, and this Venn diagram represents dogs, okay? That's a set. It's a pictorial view of a set of items. And if I have a little subset here for poodles, right? Poodles is a subset of dogs because every poodle is a dog, okay? But not every dog is a poodle. So that's what we mean when we say a subset. So a set is a subset of another one if everything in that set belongs to the large set, but not everything in the large set, say golden retrievers, right? Not everything in the large set belongs to the small set. So an example of an event here again is an even, right? Even is an event that's a subset of the event of rolling a die, the sample space here, because 2, 4, and 6 belongs to this set, but 1, 3, and 5 also belongs to it, which are odd. So hopefully that makes sense. So again, another example, single die is rolled. A sample space, as we said earlier, is 1 through 6. And there you go, there's your event, 1, 3, and 5, which is rolling an odd number, which of course we could denote just O, not to be confused with 0. So another example we can take a look at, a little bit more complicated, but not terribly, is something that comes up in craps, right? Craps is a game in which you throw 2 dice, both of which have 6 sides. So you can think about what's the sample space for that, what are the possible outcomes for that. Now in craps, you usually use the sum of the 2 numbers. The sum of the 2 numbers showing on the dice. So for example, if the 2 dice, let's say, are facing up, okay, you're looking from above, and one die says a 5, and the other die has 2 holes, right? We would add the 2 numbers, and that would become 7, right? So in craps, the event 7 means that you rolled a 5 and a 2, or a 2 and a 5, which could happen, 2 different ways. Again, if these are 2 different color dice, let's say we have a red die, right? And we also have say a green die here, then hopefully it makes sense that a red 5, right, a red 5 here and a green 2 is not the same thing as a green 5 and a red 2. So those are 2 different outcomes, okay? So the sample space for 2 dice, you think about, well, there's 6 possible outcomes for this die, and there's 6 possible outcomes for this die. So how many items are going to be in the sample space here? If you think about it, there's going to be 36 outcomes. So in this case, we use a red and a black. So a red 1 and a black 1, all the way up through a red 6 and a black 6, right? So note that here we have red 2, black 1, but here we have red 1, black 2. Those are not the same outcome because of the fact that they're different dice. Okay, they have the same sum, right? Here the sum is 3, here the sum is 3, here the sum is 2, and so on. And here the sum is 7, and so on. So what you'll also notice is that the diagonals have the same sums. These are sums of 4. These are sums of 5, right? These add up to 6s. These add up to 7s, 8s, 9s, 10, 11, 12. So in the game of craps, certain things can happen based on when you roll the die. So if you roll the die at the beginning and you get a 7, you win. Okay, but if you roll the die and get any other number besides 2 and 12, then you keep rolling the die until you crap out, as they say. So there's all kinds of side bets that can occur until you get a 7. So once you get a 7, you crap out. you'll notice that 7 is the most frequently occurring sum in this sample space. How many ways are there to get a 7? You can just count. 1, 2, 3, 4, 5, 6 ways to get a 7. Okay. So anyway, the sample space can also be, so rolling doubles would be an example of an event. Okay. So the sample space can be represented by the set of ordered pairs. 1, 1. Okay. 1, 2. This one here would be 1, 3. All the way up to 6, 6. And there's 36 of those. Okay. Now, one of the notations that we can use when we talk about the sample space is the size. In other words, how many things are in this set right here. Well, the way we do that is we say little n with the parentheses with s. What we're saying here is the number of things in that sample space is 36. So if you ever see me use the notation with a little n, I'm asking you how many things are in that set. So, for example, in this case, if we say D is the event of rolling doubles, that would be snake eyes, whatever that's called, train tracks, and so on. So 2 2s, 2 3s, 2 4s, 2 5s, 2 6s. How many things are in D? Well, if you count, there's 6 of them. Okay, which is a subset. After that, we're going to start talking about the probability of these events. Okay, a tree diagram can sometimes be helpful if you have multiple trials. So say if you're tossing a coin multiple times, 3 times, for example, 4 times, 5 times, 6 times. Let's see if we can figure out the sample space. Well, it's sometimes the tree diagram makes it a little bit easier so that it's systematic and you don't forget any of them. You don't miss any of them. Okay. So on the first toss, what are the 2 possibilities that can happen when you toss a coin? As we mentioned earlier, it's heads and tails. So let's let capital H be the event that that heads is facing up, and capital T is the event that the other side, tails, is facing up. Now, after the second toss, let's say that we got heads on the first toss. Then what are the 2 possibilities here? Well, heads and tails for this example here, right? And heads and tails for that example there as well. So now we're starting to branch out, right? It's starting to branch out. So if you think about this event right here, how could we, if we were just stopping at the second coin, what would we call that? Well, the simple answer to that would be HH, or heads and heads. So heads on the first trial and heads on the second trial. But we're going to do it one more time. So we have heads and tails all the way across. So now think about what that event would look like. That's going to be HHH. So if that's one element of the sample space, how many elements of the sample space are there? Well, the others would be, would be heads, heads, tails, right? Heads, tails, heads, HTH. Heads, tails, tails, HTT. That's that, right? And then all the other 4 from this side, right? So that's what the sample space would look like. And how many elements are in the sample space? Number of things inside S? 8. Now the number 8 is actually important to take a look at how we got 8, because if you can find a pattern, then you don't have to actually list them with a tree diagram. You don't have to list them, and you don't have to do a tree diagram if you can figure out how many things are in the sample space without actually having to draw the picture. So going back to a single trial, you have heads or you have tails, yes? How many things are in that set? There's 2. Then if I go for 2 sets, HH, HT, TH, TT, right? There's 4. And then here there was 8. So what is the pattern of 2, 4, and 8? Well, the pattern is that if we toss the coin n times, then the cardinality, so then the sample space will have 2 to the n, right? The sample space will have 2 to the n. So here 2 squared is 2, right? This was tossing it, 2 to the 1 is 2, right? 2 to the 1. Here we were tossing it 2 times, so 2 to the squared is 4. Here we're tossing it 3 times, so 2 cubed is 8. 2 times 2 times 2 is 8, right? So then we might ask a question. We might say, okay, that's really messy, so I'm going to go off of that. So let's say that we toss a coin 6 times. Then how many sample space events will there be? 2 to the 6th would be 2 times 2 times 2 is 8, times 2 times 2 times 2 is another 8, so 64. So there will be 64 events, right? So what we can do now is take that idea and apply it to probability. So the probability in an event is not a prediction of what will occur in the short term, but rather it's going to be sort of a tendency based on the behavior of outcomes over long periods of time and repetition. And computers have helped us determine probabilities so that we can use that information. A perfect example of something that's recently came up using the idea of statistics is that movie Moneyball. Moneyball, if you didn't see it, was a movie about baseball, but it was specifically about how the Billy Beane, who was the manager of the Oakland A's, he and his colleague used statistics to select players who were good and they fit together well, but the players were not popular. They had something about them that supposedly made them worth less, worth less than someone who's a star. So they were able to take their small, meager salaries and get a team together that either won the World Series or was close to winning it or something like that. But anyway, so that's one of the things that you can do with statistics. So once again, back to flipping a coin, 50% probability of heads. What if we flip the coin 10 times? How many times should it come up heads? How many times should it, or will it probably come up heads? Then we can also ask the question, how many times do we expect it to come up heads? It turns out that these two different questions have different answers. So I think you know the answer to this one. It should come up about half the time, right? But as it turns out, that's not necessarily the case. We have what we call a binomial distribution. The binomial distribution says that on average, or let's say that the highest probability of coming up heads is 5, but if you think about it, sometimes it'll come up heads 0 times, 1 time, all the way through 10, right? So we don't say that the probability is 5 out of 10. We say that we have to say something else. We might say something like, what's the probability that it comes at least 5 heads? Things like that. So we'll talk about that more later. What about 100 tosses? What about 1,000 tosses, et cetera, et cetera, et cetera? So using, multiple trials, hundreds, thousands, millions of trials, what would we expect to happen? So this is sort of what probability is all about. So the basic principle for determining probability, there's 3 basic ways to calculate probability. One of them is called subjective. So subjective meaning, it's going to be biased, right? So it's an educated guess. It's subject to the expertise of the guesser. So here's a hint. One example of subjective probability would be maybe weather reporting, right? What is the chance when they say the chance of rain at 8 o'clock. If you ever turn on your weather app for your smartphone, for example, I have an app on my phone that has an hourly report for probability of precipitation or rain, right? And I use this because I play tennis outside often, right? So if I look at my phone and it says, even if it's overcast outside, at noon the probability is 0%. At 1 o'clock it's 0%. And all the way up till 8 o'clock it's 0%. Then there's probably a good chance that it either won't rain or it won't be so wet that I can't play tennis. I'm not going to slide on the court and hurt myself, right? But where do these probabilities come from? They come from the almanac. They come from the meteorologist from either the Weather Channel or the local news or wherever, right? And where do they get their information from? Well, they use radar. They use all the expertise of all the other meteorologists, et cetera, et cetera. So, we can say with a certain degree of accuracy, is it going to rain? Also, what's the temperature going to be? Is it going to be 70 degrees? Is it going to be 77 degrees? Whatever. So these are educated guesses. These are subjective probabilities. Let me erase this. Okay. Economic predictions. Will the stock go up today? Will the stock go down? These are economic predictions. Okay, so next is the empirical probability. Empirical probability is used most often in healthcare and drug testing, things like that. So empirical probability means, you're finding it by doing an experiment. This is something that scientists do. This is something that drug companies do, and so on. Psychologists. So the interesting thing is if I apply empirical probability to coin flips, I don't know if you can read this, it's a little small. If I flip a coin 10 times, right, and it comes up heads 6 times, it turns out that the probability of heads is 6 heads out of 10, which is 60%. Okay? This is solely based on experiments. Now we know theoretically that the answer is 50%, but using the empirical rule, it's 60% in that case, just in that case. So you can see there's a major difference between doing experiments and using mathematics, basically. So the last one is the classical rule. This one's it's a little out of order. So the probability of event E, okay, using the empirical rule, is the number of times that E occurs over the total number of repetitions. I had a silly example that I used in class, which was I took my shoe off and I threw it in the air, and it would either fall on the bottom of the shoe, land on the bottom of the shoe, or land on the side. So I would say, and let's say that it landed on the bottom like 7 times and it landed on the side 3 times out of 10, right? So then the probability of landing on the bottom is the number of times that it landed on the bottom divided by the total number of times I threw my shoe in the air. It's sort of a stupid example, but it's a perfect example of the empirical probability. So 70% in that case. So once again, make sure that you know how to convert fractions to percents to decimals and things like that, because we're going to be doing that constantly throughout this course. Okay, finally, we have classical probability, which I also often call theoretical probability. This is really some of the meat of the mathematics in this course. Is the probability of an event A is the number of ways that A can occur divided by the total number of elements in the sample space. We've talked about what the sample space consists of. Okay, so what is the probability of Q, where Q is drawing a queen from a deck of 52 cards? Well, if you know anything about cards, there are 4 suits, there are 13 types of cards, ace through king, and queen is one of those types, and each type of card, each card occurs 4 times. Hearts, diamonds, clubs, and spades. So there's 4 queens in the deck, and there's 52 total cards, and so the probability would be 4 out of 52, which reduces to 1/13. So if you wanted that as a percent, let's say, then you would go to your trusty calculator and you would say 4 divided by 52. Now there's a couple of things that you can do with this calculator. You can get a decimal. Okay, so the decimal is 0.077 approximately. You can also turn that into a percent by multiplying by 100. So 7.7%. You can also take the fraction that was the original probability, hit the math key, and use the arrow frac function on the math menu, and then hit enter. And what it'll do is it'll reduce that fraction or simplify the fraction to the lowest terms. So that's where the 1/13 came from, and it's 7.7%. So these are all the same. Okay. Empirical probability. For most experiments, it is impractical to do enough repetitions. I mean, we're not going to be literally throwing or tossing a coin 1,000,000 times or 10,000,000 times or 100,000,000 times. But we can use computer programs to do these things. And we can also use theoretical probability because we know from previous experience and from others that the probability of getting heads is a half in general, right? For some information, empirical repetitions are the only way to determine probability. As I mentioned, science is one of these things. Science, there are theoretical aspects to science, but to test a theory in science, usually you have to do an experiment or more than one experiment. So blood types of the overall population, how do we know what percentage have type O, type A? What are the other types? Is it AB? I'm probably missing one. Anyway, B, I don't know. So without random sampling, it is impossible to determine the probability of an event empirically. So we have to have a good sampling method, as we've talked about before. Empirical methods use a series of trials that produce outcomes that cannot predict in advance. So when you hear the word trials, hopefully you're thinking of drug trials, for example. When a company wants to have a drug approved by the FDA, usually, as far as I know, it has to be done scientifically, usually a double-blind experiment, and so on and so forth. Another example here, what's the probability that a patient will survive after undergoing cardiac surgery for an MI, which I believe stands for myocardial infarction or heart attack, right? Well, it depends on the type of cardiac surgery. It depends on the age of the patient, right? But we can use all that information to determine what is the likelihood of survival. And then once we determine that likelihood, say if the likelihood is, 78%, we bring that to the patient, we bring that to the patient's family, and they can decide, all right, do I want to undergo surgery? Is it worth it? Okay. So we use statistics all the time in medicine to inform ourselves and to inform patients. Not that I'm in the health industry. I didn't mean us, but but doctors and nurses and other healthcare workers use statistics to inform the patient, to inform themselves about what to do in a particular case. And again, classical probability, the number of outcomes of the event divided by the number of outcomes in the sample space is the probability. So once again, capital P with a parentheses means that you are finding the probability or likelihood of the event E, which is the number of items in the event E divided by the number of items in the sample space. Remember earlier I said that when you have n, we're talking about the cardinality, which is the number of things in that space. So what is the probability of getting a heads? We said that is 1/2. We did that already. So 1/2. Because there's one head, right? In other words, one of the sides of the coin is a head, and there's a total of two sides of the coin. Now, some people might say, well, what about if the coin lands right on its side? Well, that's not likely, right? It's so unlikely that we sort of discount it. What's the probability of rolling a 5 when we toss a 6-sided die once? Well, as you remember, there's only one side of the die that has 5 holes. Again, this is a bird's eye view facing down on the die, right? Just make it easier so I don't have to draw the three-dimensional. So there's one way that you can get a 5, and there's 6 sides to the die, so the answer should be 1/6. Now, once again, remember that you can turn that into a percent by saying 1 divided by 6 times 100. 16.7% approximately. So be able to turn fractions into simplified fractions, into percents, into the wiggles mean approximately, right? Approximately. Into decimals. So decimals, percents, and fractions. Okay, so what is the probability of selecting a card at random from a deck of cards that is a heart? This is similar to the queen example earlier. There are 4 suits, so there's 13 hearts and 52 cards in the deck. So 13 out of 52 reduces to 1/4, which as a decimal is 0.25, which is 25%. So on the exams, be able to easily convert between these numbers. If you have troubles with percents, you'll need to practice those very, very soon. Okay, what if we flip a coin 3 times? What is the probability of getting 3 heads? Okay, so remember earlier there were 8 items in the sample space, and they were HHH, HHT, sorry, I did the HHT first, HHH, HHT, HTH, and so on, right? There were 8 of them. And we want to know 3 heads, which is the HHH example, right? So there's one of those 8 items that have 3 heads, and there were 8 total. So what is that, 12.5%? I'd have to check that. So again, if you look at the tree diagram, HHH was only that one, and there were 8 total. So there's HHH, which is that one, which is one of the total 8 that are listed in the sample space divided by the number of items in the sample space, 12.5%. And this concludes the video.